applications from the prestigious IIT Kharagpur, Anand brings extensive expertise in digital VLSI and artificial intelligence applications. His academic background is complemented by his industry experience with a strong foundation in electronics and communication engineering. Anand's research interests span digital VLSI, artificial intelligence, and neuromorphic computing. He has authored and co-authored over 15 research articles in reputable journals and conferences, showcasing his expertise in these areas. As a senior engineer at MathWorks, Anand collaborates with educators, researchers, and institutions across India, supporting their curriculum development, research initiatives, and innovation endeavors. Please join me in welcoming Dr. Anand as we look forward to his invaluable insights and experiences.
Thank you. Thank you very much, ma'am. And thank you, everyone. It's a full house, so very nice to see that. And yes, it's at the back. Charging is. Let's start, huh? So we'll start now. So we are around 11:35, and I know it is a long day for all of you, so you don't have any tea break now. But like the previous talk, let's try to be more interactive. So if you have any questions, and we will also try to ask some questions in between, do interact, do answer, do ask your queries, which will help you in your studies, in whatever you're working right now, or what kind of projects you would like to work on. So if the talk can help you along those lines, that will be a big takeaway for us. So I'm Anand, and with me, we also have Ramana. So Ramana is wearing the red t-shirt, so he's there. So we will be, he will also help in coordinating the session. And let me first ask us questions. So what do you understand by this topic, design and prototype FPGA and SoC systems using MATLAB and Simulink? So MATLAB and Simulink are the flagship products of MathWorks. But what do you understand by this? Anyone would like to answer? You can raise your hands, and whatever is in your mind, you can just try and give an attempt to that. No one? Oh, yes.
Very popular hardware that is, especially FPGAs, of course, they are programmable field gate arrays. So they help to design complicated systems, and especially they are programmable on the field and also flexible. It's the MATLAB and Simulink, as you said, two different packages of MathWorks. So you want to tell us how to sort of design using these systems employing FPGAs, and how to make small prototypes of these systems, etc.
Thank you very much, your professor.
Satyanarayan.
So thank you, Professor Satyanarayan, for the answer. And very rightly said, so there is the term FPGA, which is Field Programmable Gate Array. So we heard about semiconductor in many areas in the previous talk, especially in the automotive applications, the ECUs and so on. 1,000+ chips are used for different purpose. FPGA is one such semiconductor device which you can program. So whenever you are designing your system, you can program it, reprogram it again, and you can finally go towards the further fabrication or ASIC implementation. So Ramana, can we have a goodie for Professor Satyanarayan? So we have a very limited set of things, but okay, I think that will be better. Ramana, I think T-shirt will be better. I think. Uh, so. So Ramana will help me evaluating. So if you are close to a right answer, even if you are attempting, there is a chance you win a goodie. Okay, so this is just a complimentary thing. So now let's see if this video runs. Okay, it's running. So try to observe this, what is happening here. So we have a FPGA board that we just discussed about. The board is connected to the computer. And inside the computer, you see some simulations happening in a simulation environment. So there are a couple of blocks that you see here. So at the bottom, there is one block. At the top, there is another block. And we are trying to program something, the device itself. So you see FPGA programming file loaded successfully. So the FPGA which is connected, that is programmed through the software, through the simulation software. And then we try to run this particular model, the entire model. And we have a plot like this. So what is this plot doing? If anybody can just see the plot, the legends, and try to attempt what we are trying to do in this plot. What are the three different, or you say three different signals? Anyone, you can raise your hand. We can take some mic so that you can answer easily. And here is the motivation for you. Oh, here we have one. You can tell your name also, and then you can.
Nitya, I think the first graph is based on frequency.
First graph is based on frequency and okay. Thanks for the attempt. So there is no harm attempting it. Although it's not the right answer, but it's okay. You can make any kind of attempt, whatever you think. I have not explained anything here. Yeah, that is still close to the what we are trying to do. So okay. There is a reference, and we are trying to compute the error between that. So I think, so what is your name? Gopishan. Acha. So that's the right answer. You will definitely get a goodie. But anybody wants to add to that? Difference of two signals. So similar to what Gopi mentioned, that's right. So now if you see the legends on the top center of the signal, FIL, okay? Then we have DUT ref, and then we have error. So the error, the third signal is the difference of the first and second signal. FIL is, okay, I can ask many questions like that, but let me tell these things. FIL is FPGA in the loop. Okay, so whatever output you are getting out of the board, so we are visualizing that signal in the simulation environment. DUT is design under test, the reference block. Okay, the initial architecture that in the simulation environment that we have made, and we are comparing whether we are getting the similar kind of results after the thing is running in the hardware as well. Okay, so that is a kind of verification of our algorithm with the algorithm in the hardware. Okay, so now let's see some of the questions that we want to address through this tutorial. So it is around how we can reduce the development time. Okay, so whenever you are doing any project in industry or even in your courses or in your final semesters, you will have some limited amount of time to do something. So you have to decide the type of project, decide your team members accordingly so that you can complete to some extent. So how to reduce the development time of your project? That is a question. Can you read the code? Can you edit the code? Okay, so we will come to the second point in a bit. How you can optimize your design. Okay, so whenever you are doing any project, okay, it's not only one way you can solve it. There can be several ways to solve it. So that is what is optimization. So what are those parameters which can help you to optimize that? And finally, how quickly you can verify the hardware. So in the first video what we saw, we were trying to verify something. Okay, so that's a kind of functional verification, verifying the functionality of the algorithm and the algorithm running in the hardware. So these are the 4 questions, and so let me ask another question at this point. How many of you have used MATLAB before or are aware of MATLAB? You can all raise your hands. I see 1, 2, 3, 4, 5, 6, very few out of the entire audience. Okay, so okay, all are first year students. Okay. Okay, then let me ask an even simpler question. What is the full form of MATLAB? Anybody? You can just raise your hand and then make an attempt. Do not try to do a Google search now. Okay, I see your hand raised. Matrix Laboratory. Yes, it's correct. So Ramana, we can have one. What is your name? But that's okay. That's okay. So for the first year students, you will be learning MATLAB through your courses like Introduction to Programming or Introduction to MATLAB. So MATLAB is a matrix laboratory, and it was founded long back around in 1984. So there was a scientist, Cleve Moeller. So it was part of his PhD thesis, and later it developed to a commercial company known as MathWorks. And now we have so much additions to it. In fact, 70% of our users are in the automotive industry. So you saw the importance of you saw the different technology trends in automotive in the previous talk. So they use our tools heavily in different ways to make that system. And here you see another thing. So like HDL coder and HDL verifier. Okay, so what is this HDL coder and HDL verifier? Maybe the full form of HDL, and if you can add to it. Anybody? Hardware description language, that's correct. So, and would you like to add to it? Like, what is this HDL coder, HDL verifier? Any idea? Correct, correct. And with verifier, for verifier? Okay, so that's, we can verify the logic of the digital circuit. That's correct. What is your name? Nagalina. Yeah, thank you for the answer. That's more or less correct. So when you are writing any program, whether it's C, it's a C language or any language or a MATLAB language, that's your algorithm. Okay. And when you are talking about semiconductor hardware, the chips to work, okay, then we have to write a hardware description language, HDL, like Verilog or VHDL, which is actually programming the architecture. So you need to have knowledge about VLSI. So good to know about the different VLSI programs starting since 2003, and you will be learning more on how you can go from algorithm to your architecture. And inside VLSI, there are so many topics. So you can study about circuits, whether it's analog or digital. You can learn about devices, okay, which is forming the transistors used in their circuit. And finally, you go to the fabrication part, okay. So with Coder, you are basically programming the architecture that is with you, so that it can be realized in a hardware, either programming an FPGA or programming ASIC device, application specific integrated circuit. And verification is nothing but verifying that thing. So it's not a small part. So if you look for job, means through placement or outside placement in this domain, at least 50% of the job will be on the design side, where you need to understand the architecture and write the code for that. And the other 50% will be on the verification side, where you are verifying the design, okay. And most of the job in India you will find in the verification sector. So that's a very important area to know about. So that was in general. Now the HDL Coder and HDL Verifier, these are just toolboxes. So like MATLAB Simulink are the software, we have a lot of toolboxes with us. So can anybody make a close guess how many number of toolboxes? So it's just a number that you have to guess. Similar to the number of ECUs that you were guessing earlier. So how many toolboxes we will have in addition to the MATLAB Simulink software? So you can raise your hand, try a guess. We can give 3 attempts. The first 3 people who guess, whoever is closest to the answer wins a goodie. Nobody is raising their hand. I see few people searching their mobile phone. 1200. Okay, that's a big number. Second guess. Okay, you answer 600. Okay, then let's see the third one. 60. Okay. 12.
Oh my God, the variance
Okay.
is so high.
So we have different answers, 1660, 20 to 25. Okay.
No one is close so far.
No one is close, but 2 to 5. Okay. 4 to 5. Okay.
Oh my.
8 to 10. Okay.
One clue, 3 digits.
100 was with a clue. Acha, so okay, so 100, I think that is the closest. Before that, I think 60 was the closest one. I think you answered 60 and they're 100.
Someone told 150. That's the closest one.
Okay, so Ramana, you decide.
Yeah, the 150 guy.
So we have around close to 130. So it's like somewhere between 120 to 130 toolboxes at this moment. And this HDL Coder and HDL Verifier, couple of them. Okay, these are 2 toolboxes catering to this segment of HDL code generation and verification. Okay. Okay, so this is the overall agenda that we have. So I will, okay. So I will try to cover some of the traditional, because most of your first year, I will try to keep it in a higher level. So what is the traditional implementation workflow, and what do we mean by this model-based design approach? And then we will deep dive into how you can use this HDL Coder Verifier in your project works, because that is where it will actually help you. And finally, what is optimization, how you can make your design better with lot of resources, both for students and faculty. So I will, whenever we have some resources to share, I will just highlight it and you can let it know. So one such resource will be a kind of a set of files for all of you. Okay, so you can explore these things after the tutorial. So basically how to get started with HDL Coder, how to make simple circuits, using your logic gates, Boolean logic gates, and make a filter and realize the similar thing. So you can make a note of this URL. This is one of the resource for all students, faculty member. It's a tiny URL web page. You can download the files what we just saw earlier. And if you have any questions while you're exploring that, you can always reach out to me or Ramana. So now you can see some more toolboxes like machine learning or deep learning, control systems, and so on. Okay. Next, another question I like to ask all of you is about Simulink. Okay, we just saw MATLAB, and it is basically a numerical programming environment for you, where you can develop your algorithms. Okay, visualize in terms of plots, and do data analysis, a kind of thing. But the second flagship product, which is Simulink. Okay, so what is Simulink? How many of you have used Simulink or know about Simulink? If you can raise your hand. I see one hand, two hand raised. Okay, both of you can start first. It provides graphical interface. That's correct. Okay, and you can do some sort of model-based designs. Both the answers are correct. So Ramana. Oh, you already got one hand. That you didn't get anything. I think Ramana, we can give one hand to you. So it's a graphical environment. So that's correct. So it will be a blank page where you can pull in different kind of blocks together, and you can make connections to it. And we will come to what model-based design is. So it is the environment where you can do this model-based design kind of analysis. So one of the main advantage of the Simulink environment is it is a very easy to understand environment for multiple engineers working in different domain. They can visualize their system in terms of different blocks, sub-blocks. It can be connected, and you can test your design. You can simulate, verify your design. It has dynamic solvers beneath it, which can do dynamic simulations. And after that, you can also generate some production quality code, whether it's a C code or whether it's HDL code, depending on the target hardware, which is used by the different industries for deploying in their hardware. So this is the main advantage here. Now, you mentioned about model-based design. So this is how a model-based design chart looks like. So you start with your research problem, your requirements, and then you have to work on your design, which can be done either through your MATLAB algorithm or through the libraries inside the Simulink block. And after the design is finalized, you can go to the implementation stage. Okay, implementation means how you can translate that design to the target hardware through the different coding languages. Okay, so if it is a processor or a microcontroller, C++ will be the code. If it's a FPGA ASIC, VHDL Verilog will be the code. So that implementation phase is to be done, and then you have to integrate all of them together. So while you are going through all these stages, you are testing and verifying to remove the error in the early stages. So this removal of error early on is important to reduce the number of iterations. Okay, because this is not a one-step process. You have to iterate many times so that you can finally get a desired output. So that's how you save your time, as well as it is easy for different team members working in different departments to work and collaborate together through this model-based design environment. So that's why most of the examples that you will find in the exercise will focus on the Simulink environment. So you will start building the simplest circuit inside your Simulink environment and go through the entire process, which we will discuss. So this slide I will skip. So it is just telling more about FPGAs. So it is reconfigurable, and You can achieve higher speed due to parallel processing, and those are the characteristics of FPGA. And system on chip is just an add-on to FPGA where you also have a processor with it. So FPGA is like programming the hardware part, so the programmable logic, and the processor can be maybe ARM processor, which is like the programming system part. So PS and PL, if they are together inside particular dedicated hardware, that is known as system on chip. And when we talk about FPGAs, so there are specific vendors. So for example, if it is AMD or Xilinx FPGAs, so AMD has acquired Xilinx, or if it is Intel or Microsemi, so all these are manufacturing these hardware boards. You will have a corresponding software for it. Okay, so you need that software which will help you to go through these steps like synthesis, place and route. Okay, so when you have written your HDL language and you have to generate the final bit file, so it goes through a step of processes, lot of steps like these things, for which you need that software. And you can how you can achieve higher speed, because you can make your design in many ways. So you can do parallel processing, and it is a dedicated place to run your algorithm. So when you compare it with a CPU, so if there are 10-20 applications running together, those are not running in parallel. So each instruction will run it sequentially, so the speed of operation will be less. So that's another thing. And there are some limited set of resources. So in FPGA, because the hardware is fixed, so there will be limited set of memory, there will be limited set of the DSP blocks or the lookup tables, input output pins. So whatever resources you have, so you have to fit your algorithm within that as well. So with that, I will ask one question. So when we are optimizing the design, so what are the different parameters which we can optimize? When we are optimizing a semiconductor design, you can say, what are the different parameters in VLSI optimization? Okay. Okay, so I heard one answer. Can you raise your hand? Power area delay. Okay, that's correct. So thanks for answering. Okay, you already got. So, but I think, yeah, like most of you are from first year. You want to answer? Yeah, please. Delay. Reliability, performance. Yeah, these are also important parameters. Reliability, performance. So power, it's very critical because it will depend on the type of application also. So if you have limited power availability, power becomes very critical. Speed, so how fast your application can run. If it is a high speed application, so speed will be an important parameter. And area, of course. So these are the three things which are very important. And then the reliability, those are the additional things which will come into the picture. Okay, so if your application is related to a space technology where you are making semiconductor chips, so you have to assess the environment there. You have to use proper semiconductor which can tolerate the radiation or the environment in those cases. So in those scenario, reliability will be another thing. And of course, with all these, the performance has to, you cannot compromise with the performance as well. Okay, so that is an output to that. So speed, area, power, reliability, performance, all these are there. So with that, if you see here, we are listing two of the parameters here, which can be optimized with the help of the tools. Okay, because there are many software tools which is helping you to do the optimization. So speed and area are two such parameters which can be optimized through this HDL coder functionalities. Okay, and when you are optimizing, then so the 5 dots that you see here, iteration 1, 2, 3, 4, 5, are the 5 different type or 5 different iterations you go through the same process when you're optimizing your design.
One second.
Huh.
Yeah, please, if you are not interested, you can leave the hall. Please do not sit here and talk. If you are not interested, please leave the hall. Okay, so there are people who would like to listen and it is disturbance for them, right? So please value our time and others' time. If you're not interested, please leave. Thank you.
Okay, so I think you don't have a tea break in between, but all of you who are interested, please try to ask your questions also. So I may discuss relevant points accordingly and slightly change the mode of talk. And so in this particular slide, you are seeing the different, there is the acceptable solution zone. So only in the 4th and 5th iteration, you are within that zone. So you can meet the speed requirement as well as the area requirement. So that's why optimization is a very important aspect. Okay. And then you see the power and something known as fixed point precision also coming into the picture. Yes. Yes. So there are specific optimization algorithms, so which run in the background. So there are theoretical things. So for example, if I talk about speed, then there are optimization techniques like pipelining. Okay, and inside pipelining, there will be different types of pipelining. So you have to know about which pipelining technique you have to apply, which can improve the speed of your architecture. And those things will be applied in your architecture. Yes, yes, yes. Correct. You can choose that. You can choose the different types of optimization. Similarly for area. So if you want to share resources, you can choose which kind of resources you want to share, whether it's an adder or multiplier, and those things will be shared. So with that, you can make a circuit fully parallel or fully sequential. So that can be chosen.
So while generating code, you can set objectives, whether you want this code to be efficient performance-wise or the speed-wise or the memory-wise. You can set those objectives and generate code for that. Right? So that way you need to make a trade-off basically on how much fixed point precision you need, how much power that you can bear, so that probably that green color area you would like to be, that's where you would like to be, and then based on that you need to set your objectives.
Yeah,
Go ahead, Anand.
Thanks for asking that question. So let's see if I can show you that in some time. So where you can change those options as well. So before that, so this is one slide which is showing you how you can make your algorithm, how you can develop your algorithm using MATLAB functions, using the Simulink models. There are state flow charts inside Simulink which can help you build controlling algorithms, as well as some physical models inside Simscape. Also there is AI everywhere, so there are some deep learning networks also which can be used in this area. And when you are making your design, you have to make sure you use the correct functions. So most of you will be learning MATLAB, so it will be a very simplistic environment to write any kind of code using any kind of functions. But this is a specialized topic. So when you are building your systems, you make sure that you use the correct set of functions. So there are only limited set of functions like 200 or 300 plus Simulink blocks, which is compatible for HDL code generation. So only if you use or build your system correctly, you can make use of the facility of code generation and build on your design. Okay. So this will be exercise 1. So you will explore this later. So so what is this here? What we are trying to do? Can anyone say what kind of gate is that? AND gate. Okay. So all of you are aware of AND gate? Okay. So in the exercise 1, you will just simulate a simple AND gate in your Simulink environment, and you will go through the entire process, okay, of code generation, how you can generate the HDL code of a AND gate. A very simple thing, but it will help you get familiar with the tool. Similarly, there will be a part B to it, where you are using a delay block. Okay, delay block are like memory elements which can store either a 1 or a 0, flip-flop registers if you have. So you will be learning those in your upcoming courses. So you can do that as well. Okay. Now, let me emphasize on one of the use cases in industry. So Rambus is a company. So they made their DSP algorithms, DSP blocks for their ASICs. And here, the important point mentioned by the director of digital engineering is that they had that both design and verification teams, and the design team will take its own time to complete the design, and only after that the verification team can start verifying it. So they used HDL coder functionality to get a first level code with the generated, which can be used by the verification team. And with that, they can save time for both the design and verification. They can work simultaneously. And at the end, it was seen that 80% of the generated code was retained in the final implementation. So that's a very big number in terms of not only saving time for a first-hand verification, but actually using the 80% of the generated code. So similar takeaway should be with you also. So when you are learning to generate the code, it is not that you should not learn how to write or how to learn about Verilog or VHDL code. So in your courses, you will be learning that, and that's a additional, very important skill. Okay, this is just helping you to aid in terms of building bigger projects, okay, where you can make use of both the knowledge. Okay, so you should know both the things, how to write code and how to generate code. Then in the same thing, exercise 2, you will be working on examples like half adder. So how many of you have studied this course on digital circuits, where you study about half adder, full adder? If you can raise your hand. 1, 2, this side. 2 only. Not in first year. Okay, so it's a early resource for you. You can keep it with you whenever you are studying in your course. You can explore more on this. So you will be learning like circuits, combinational circuits like adders, or sequential circuits which has those memory elements like counters, and you can work on those examples. I will skip this as well. Then here are some more use cases. So one in the communication industry, where they have made their open radio access network, and here it is from Capgemini, and what Vinod Suravas from the team is telling, they modified their design. Okay, so they used a shipping example, and they modified the design to meet the customer's requirement, which helped them save a lot of time. So there are a lot of shipping examples which you can also use for your projects. Similarly, on the right, you see it's a company, a biomedical, a company which is analyzing the ECG signal, the heart signal. So they are very good at developing their algorithms, okay, the filter algorithms for removing the noise from the ECG signal. But again, to translate that to a processor, okay, they use the embedded coder, the MATLAB coder, to generate C code to target it to an ARM Cortex processor. Okay, so again, these are a couple of stories in the communication, in the biomedical side. So you can relate it to different projects. So now this slide, let me just show you a glimpse of what HDL verifier is. So that's the entire toolbox. And what we saw in the first video is the FPGA in the loop, FIL. We saw the term FIL. So where we are doing a verification with the FPGA board itself. Okay, so it's a functional verification. there are many different types of verification. So before the board also, if you have a software, a logic simulator, so you can use that logic simulator to run the HDL code and do a comparison. That becomes a first level co-simulation, a behavioral check. Then you have other techniques like FPGA data capture, XI manager, system Verilog DPI component generation. So these are some advanced techniques which will help you to generate the C code out of it, and you can use it in the other EDA tools which are doing extensive verification processes. Like UVM is one of them, universal verification methodology. And all of these techniques are saving some time in terms of generating the test cases. So in a very simplistic way, if I have to say, whenever you are testing something, there has to be different kinds of test cases around it. So it's not that if you are testing for 1 or 2 cases, your design is passed and it's a well verified design. So how to generate those test cases? So that itself is a task. So in those way you can generate the test cases and you can generate those DPIC code for that. So these are the different scopes of aiding in the verification side. And this is another story from a ship company. So they are building their power electronic devices, so very expensive things. So if once they deploy the hardware and if it doesn't work, it's a huge loss in terms of money and time. So they do a lot of verification, the FIL testing of that system before they go towards deployment. Okay, Leonardo is this company. And now coming to this slide. So this is showing the traditional implementation workflow. We start from the algorithm to the architecture, and the very first step is fixed point conversion. Okay. So what is fixed point conversion? Or why do we do it? Anybody who has not answered yet, or you can tell. Some fixed point. At some point, can you just tell again? At some point, the process must start. Okay, it's not exactly that.
Not the answer. Probably the research scholars or faculty who are here.
I think it will be difficult for the first year students, so
Yeah.
don't dishearten yourself. But
Yeah, it's digital signals. But if you use CPUs, I don't usually need to go to fixed point conversion.
In the fixed point representation, you need to specify the sign of the number or some word, and you need to specify the decimal number, and each, if you are having a 2 register, each 2 registers should have the same fixed data types. Maybe.
yeah, that is correct in terms of what is fixed point. That is correct. So how a fixed point representation looks like. So there is a signed or unsigned bit. There are some integer bits. There are some fractional bits. But just going one step before. So whenever you are writing any algorithm, if you see the data type in your workspace, you will see something like double or something like single written as the data type. So these are all floating point arithmetic. Okay. So what is floating point arithmetic? It is more computationally intensive. Okay. It has its own architecture. If you study about floating point arithmetic, so there is something known as mantissa, something known as exponent, and it can give you greater precision compared to fixed point, but it is at a cost of higher computation. So that's why we are going from floating to fixed, so that we can reduce the amount of computation, because we have ultimately a limited set of resources, a limited set of speed which can be supported by the device. So while we are converting from floating to fixed, we have to make sure on the performance also, so that we are not compromising the performance to such an extent that we are not getting any correct result. So this is one thing we have to take care of. while doing the fixed point conversion, but it's an important step to reduce that thing. And then the process starts. So we have to write the target hardware code, the HDL code creation part, verify it, refine it, that's the iteration, verify the different types of verification, and finally we can come to a design which is satisfying our constraints. Okay. And in this process, there are like two things happening. So there is a system designer who will be focusing or who will understand the algorithm better. Okay. And they will build the algorithm, and they will have some FPGA kits with them, but they will give that algorithm and the FPGA specification to a FPGA designer. And what the FPGA designer will do, they will try to rewrite the algorithm, or they will try to make the architecture of the algorithm, which is the RTL of that. They will write the HDL code in a simpler word, and then they will verify it through all the different types of verification. And finally, when they are implementing the design, they will see whether they're getting similar result or not. And if not, they have to again tell that this is not possible, if there can be any flexibility from the algorithm side. So it's a process like communication between the algorithm designer and the hardware designer. And that's the traditional workflow. So with model-based design, what is happening here? So the algorithm is made in the tool, and then we are automatically generating a HDL code. So when we are generating a HDL code, that HDL code will be like it will save a lot of time in terms of building the architecture and writing the code. And you can do the verification after that, the different stages of verification all together. Okay. So, and the entire thing, if you see here, so it is doing that functional verification, FPGA in the loop verification, the first video that we saw. And in terms of saving time, so we are talking about saving time, saving development time. So where are the places we are saving time? So this gives the comparison between the manual coding and the HDL coder part. So the HDL creation part, that's a big chunk of time saved there. The HDL verification part as well, and the iteration also. So when we are iterating it over time, we are saving a lot of time. And with that, we can spend more time in designing the system. Okay. So that's how you are saving a lot of time when you are using these tools. Yes, please, sir.
HDL?
Oh, yes.
The
So,
other bits I understand.
okay, so your question is why is this green portion more
Yes.
for the HDL coder?
Yes.
So the green portion is the detailed design portion. So where you are not yet started to take help of the HDL coder. Okay, so you are making your design. Okay, so you can spend more time to make a better design, which is HDL code generatable. So because the HDL code generation will happen by the tool. Okay, so that it's a specific set of time. So you do not have to spend more time there. You can spend more time in making your design. So that's why the green space is there more, so that the user can spend more time in making a better design in the better algorithm. So if you see the detailed modeling portion, time increases, and because of the development time after that reduces. So these are some features. I will just skip this part, and this slide again shows you the different code generation aspects, whether it's targeting microcontroller unit or a SoC or a FPGA block. There are embedded coder, HDL coder workflows, and this is how the model-based design helps us. Now, this is another important slide. So why we are focusing on Simulink? So basically, we discussed on a couple of things, but when you are going for optimization, you will be able to see your optimized design also. You can see the data type propagation if you are applying those techniques like pipelining, like you were mentioning how we can optimize those things, you can see the placement of pipeline registers. Okay, so there are many advantages of Simulink, which helps you to develop an optimized design as well. So with that, you will have the final exercise, the third exercise in your that folder that you copied, and this will be relatable to what you saw in the video actually. So that's a filter, that's a low pass filter. So filter is just like, if you can see the mathematics of a filter, it's the impulse response in Z transform, it's a third order filter. And if you see the mathematics, it has some adders, it has some delay elements, and it has some multipliers. So with these adders, multiplier and delay element, you can build many different types of filters. Okay, it's a very important topic in DSP, digital signal processing. And you can quickly make a filter with these blocks, any type of filter, simulate it, and go through the entire workflow. Okay, so that you can understand the different steps here. Now, sorry. So what is this? So if you see this Simulink environment, so on the top is your filter. At the bottom side is the a generated block. Okay, this is doing a first level of verification, co-simulation. So whenever you make your filter and you want to verify the HDL code, okay, that is generated, if there is a co-simulator software available, even without the hardware, you can do a quick check. Okay, so in that case, you have to just load the HDL code into the co-simulator, and this is the QuestaSim by Mentor, where you can see the input-output responses and finally see the comparison between the simulation result and the design under test. And this is the one which we saw, the second type of verification, functional verification, where you are connecting the FPGA board directly. So let us see it again. So now these are the things, now at the bottom, these are the things which is generated, the bottom block. Okay. And then we are loading it. Okay, and then we are comparing it. So now, so when you will be trying this out, you will have multiple questions like how to get started. So one of the things that you should just know about, you have a thing known as HDL Workflow Advisor. Okay, so it's like a step-by-step guide. So on the left side, you will have the different steps mentioned, how to proceed. For example, setting the target device. So you can set the target FPGA board there, select the target workflow, and then you can, you will go to step 2, which is like preparing your model for code generation. So here you have to, it will check whether your model has used the correct blocks or not, whether you have used the proper settings or not. If not, you have to change that. It will also give you suggestions. Once the second step is passed, only then you can generate the HDL code. So it's not that whatever you have designed and you can just generate a HDL code. And once you are generating a HDL code, that will be a production quality code. So after step 3, you can move to step 4. So this is the FIL implementation. So that's why it is also doing the verification part here. But there are workflows where you can do generic code generation also, just to see the resource utilization, okay, in the step 1 itself. So all these steps have been executed. So you see a green tick there, and on the console you see the different files getting generated. And so it's the same thing, but for a different design. So you can make different types of filter if you once get introduced to it. So this is the bit file that is getting generated. So this bit file is getting programmed to the device, and then you are doing that verification. So once you are comfortable with a simple example of a filter, you will get more confidence in applying it to different projects. So you can build or think of building different systems. So the main idea here is, if your interest area is can be in multiple applications, maybe designing a controller part in the communication side, or in the signal processing side. So you can focus on the system design and then use the similar workflow for testing it. Okay. So this way you can see the different blocks inside the filter, and you can verify it. So this is like running in real time. So this is just a screen grab where your board is connected. So it's running side by side, just checking the things.
So if you see, especially for first years, I know it is Greek and Latin for you when it comes to HDL, but try and understand, Anand actually started with a simple math equation or a simple logical equation, right? Which you can realize with your textbook, pen and paper. But to see that functionality on the hardware, you need to go through these steps. Okay? You use that math to model things in Simulink. There is a way where you can generate the code automatically and then deploy on the hardware, and also see if the simulation result and the hardware result are same. So that whatever you learn theoretically, you can actually evaluate that on the hardware. So you're going from math, software, and hardware. Okay? This is a very, very important skill. And you have access to all the tools in VNR Institute to do this. Okay? You have the same set of tools that Tesla has, NXP has. Now imagine what you can do with MATLAB and Simulink. Okay? So when professors teach you some theoretical concept, try to look into how to align that to this workflow. Whatever the knowledge that you gained, the math or the software, try to put them in practice and deploy it on hardware. Right. Anand, is there any workflow that you summarize from start to finish?
Yes. So
if you are aware of deploying HDL code with other tools, like they just write manual code with Vivado and you deploy an FPGA, the MATLAB and Simulink way,
okay,
summarizing
yes.
it.
So the workflow is, let me. So this is the workflow advisor. Okay, so this is HDL workflow advisor. So I will also try to show in a short while from where you can get this. And through this advisor itself, you can set the target, you can generate the HDL code, go through the synthesis process. And here is the place where you have to mention the Vivado software also. So one important point, because you're familiar with Vivado, you have to install the right version of Vivado compatible to MATLAB. And you have to link that inside the first step itself. So what is the synthesis tool? Because we are just helping you to generate the code and helping in some verification aspect. All the synthesis process is happening in the EDA tool. So we are all linking the things in the first step, then checking the code, generating the code, verifying it. So this is the entire workflow through a single advisor. So I will show you, it's under the HDL Coder app itself. So Now there are just few things in the slides. After that, I will try to show you from the MATLAB window as well. So, like we were talking about HDL coder, there is something known as HDL verifier app as well. So if you already have a handwritten code and you just want to verify it, then you can use the verification HDL verifier app and use it to verify your code. So you can build your models here and as well as do the verification. These are some general apps inside MATLAB. So for first year students, whenever you are learning MATLAB, you will be introduced to this window with a large set of apps. So I have just marked one of the app like filter designer. Ramana mentioned a very important point, like when you are learning mathematics, you are able to make simple blocks just to represent that mathematical equation and learn and actually see things work out. But these apps are helping you to, again, save some time to build complex things. So if you are making a filter of a higher order, maybe 50 order, 100 order, instead of building all the blocks manually, you can make use of these kind of apps. Just mention the type of filter, low pass, high pass, or any other thing, the order, and you can take it to the Simulink environment to work further on your project. So this is one such app. So this is how it will look like. You can see the frequency response and you can do some quantization as well. So some call for actions is like try to explore these workflows. So we have shared one set of files. We will also be sharing the deck with Dr. Padma ma'am so that everybody of you can go through these things and practice with some basic circuits whichever you are learning. And if you face any issues, feel free to contact us. We will be happy to support you. Let me see if I can. So this is on the optimization side. So I will just quickly. So we discussed about the speed, area, and validation earlier. So these are the parameters that we want to optimize. And so so pipelining. So how many of you are aware of this term pipelining? It will be very few, I know, but just 1, 2, 3. Okay, so pipelining is just one technique, okay, a very known technique which is helping you to speed up your design. Okay, so for example, you are a group of students sitting in this row, and you have to pass a notebook from this end to that end. Okay, so if you pass it to your next student one by one, then what happens is that you can pass a second set of notebook also just after you pass the first set. Okay, so after some time you will see that you are able to receive a book every 1 second. Okay, so that is what pipelining is doing. So between your blocks there are some clouds. Okay, there are some registers. The clouds are your combinational logic. These registers are like the persons who are acting as a memory element. They are storing the ones and zeros or holding the notebooks and passing to the next element. So that way you can have a smaller critical path and you can save and increase the speed of operation. So this is one technique. And when you apply those techniques through the results section, you will be able to see improvements. So for example, this is the critical path delay 68 nanosecond, and this is some area like 50 multipliers are used. In the properties section, so you can choose the optimization type. So if you go for a sharing factor or area optimization, you can reduce the number of filters from 50 to 10, okay, because you're sharing the number of multipliers. Similarly, if you are going for pipelining techniques, like here you are using distributed pipelining with pipeline registers of 2, you see a critical delay reduced from 68 to 90. Okay, the same process you are doing, but with different options. And you can see that in your high level results. And then you can see the generated version of your model as well. So in this generated model, you see there are the yellow blocks. These are the pipeline registers, okay, which is automatically placed depending on what you have chosen. So that was one of your question, I think. So how to do optimization. So this is how it is happening. So very quickly, I'm just telling about it. So for faculty members, there are faculty members here as well. So we help them to in the teaching materials as well. So if you are teaching any of these courses, just let us know. We can share some relevant script which could be taught to the students. For example, related to the topic, we have things on digital system design, which covers basic content like gates, combinational sequential towards digital code generation. For DSP also, we have few of these. So, and then there are all resource materials. So some video materials, some self-guided tutorial, okay, which will give you more in-depth hands-on experience in learning about these topics. And finally, some other toolboxes. So at the beginning, somebody mentioned like 100. So we have around 120 toolboxes. These are all different 5 more toolboxes you see. So one focusing on the vision side of applications. Okay, one focusing on the deep learning, wireless, DSP, and SOC block sets. So all these toolboxes are there with multiple other examples specific to the topic. So, and then video recordings as well. So all these will be resources. So now we can take question and answers. So we have time for question and answer. And meanwhile, you can all scan this thing and also let us know your feedback queries through the feedback form. This helps our marketing team and us to plan better on future seminars. How is MATLAB better than other software like Xilinx LT Spice? So here we are not comparing with Xilinx, Vivado. Rather, we are working with Xilinx. Okay, so we are like, you can say you have to install an add-on, okay, for Xilinx or AMD. It's known as the hardware support package. Then you can integrate both the tools together. And inside MATLAB, you can comfortably make your system. So from a system design perspective, you can make your system, verify it, and then you can generate code and verify with the Xilinx tools, okay, in terms of saving time. So if you are working with Xilinx, that's totally fine. So it's only thing is that here when you will save some time in terms of system level analysis. MATLAB with LabVIEW, I don't think so. Ramana, laptop will.
There is some integration possible with the DAC cards, data acquisition cards from National Instruments, right? It's there, but it's more around data acquisition rather than using it with LabVIEW. You can acquire real-time data through DAC cards, import that to MATLAB, and then use all of the toolboxes for it, right?
Yes, we require some libraries from them. So, like I mentioned, like we support boards by most of the boards, not all I would say, most of the boards by AMD, Intel and Microsemi. So we need to install a support package which will have the board definition files. So that can be installed from the add-on section. And once that is installed, we can see all the board names in the very first step of Workflow Advisor, where we can select that board. And based on that board, all the analysis will be done. All the code generation, verification, bit file synthesis that we are doing will be done. So we need to install that. That is an important step. Yes. हाँ. Okay. So design your own board in the sense you want to go for ASIC, uh, not ASIC. Uh, your own board.
But do
Okay.
you do that? Do you have the instances where you have your own FPGA boards?
Yes, yes, that's what I was saying.
Right, without using any Vivado sort of IDEs.
Yes,
You have your own IDE as such.
yes, yes.
Right. Generic HDL code generation is possible.
Okay.
And then you can generate the bit stream with respect to your own IDEs.
So-
Basically, MATLAB and Simulink is operating at a different
Higher
level
level.
of abstraction,
Uh-huh,
right?
uh-huh.
And the main idea why you use MATLAB is at the design phase, you have a provision to generate code automatically from your design
Yeah,
to
the
save
code,
time and also verify upfront.
Okay.
You need not wait till deployment to see whether this code is going to work or not.
Okay.
But you can verify that at the design phase itself.
Okay.
So early verification will enable you to identify the bugs.
Faster.
And then it is faster to get to the deployment.
Excellent. Yeah, that was my question.
Thanks.
So for people who are pretty new, first year students, there's a web page that MathWorks actually maintains for VNR Vignan Jyoti. Okay, you can just type in Google VNR and MathWorks. It will take you to this page. It's a portal for you. So please create a MathWorks account and you can access all the courses as well as the software by using your VNR mail ID. Okay, your mail ID is the license key. Okay. So start exploring that and it will really give you an edge. If you have that knowledge now, subsequently in second, third and fourth years, you will be using the MATLAB and Simulink in courses. Okay. So this content will really help you. Always think in terms of applying your knowledge on the hardware. It's not just software. You can't just stop with software. Try to integrate your ideas into hardware through HDL code generation, or as simple as you can use Arduino Raspberry Pi to generate code, C++ code, and deploy it onto those boards. Okay, as first years, you might be using Arduino, right? You can also use Simulink to generate code and deploy it onto hardware. Explore this, it will really help you when you get into industry. Thanks, Anand.
Yeah, thanks, Ramana. Any other questions before we break for lunch? That's it. Okay.
Thank you, Anand and Ramana. Coming all the way from Bangalore and addressing all our students. Actually, we are having only private college in AP and Telangana. I can proudly say that we are having campus-wide license. Okay, you can access MATLAB by using your mobile also. Okay, by using cloud platform. Okay, I request all the first year students. Actually, whoever is feeling hard of calculus, all those things, you can play with MATLAB. Okay, LDEs, all those things are nicely explained. You will lose your fear of mathematics when you are working on the tool. Okay, I request all the students, please sit in the lab and try to explore where you are having problem. Not only mathematics, you are having circuit theory also. You can effectively implement all Thevenin theorems, nodal analysis. Some of the students yesterday mentioned about the problem of understanding of nodal analysis, sign convention. Okay, so please, you have to sit in the system and work for that. Only seeing mobile and answering question paper, it won't fetch anything. I request all the students, try to take pen and paper, okay, so that you learn more. Even though you're having smart gadgets are available, it is not possible to reproduce. Whoever is practicing, when you want to win the game, sports, okay, how they will practice. If you want to success in your life, this is the right age. I request all the students, make use of the facilities that are there at VNR. Okay, so if you want anything extra also, we are happy to provide. Okay, Ramana is very close to us. So he is also senior engineer in education. Okay, he will guide us.
wherever you are having problem. So exclusively Anand came from Bangalore to address all of us. Okay, I request all of you, please come forward to learn. Okay, simply sitting in the class without attentive, okay, it is no use. Okay, I already mentioned yesterday, always you should be proactive, then only you can learn more. Suppose if you are sitting ideally without listening to your teacher, teachers won't read anything. If you want your teachers should be smart, that is in your hands. You should ask more questions so that they will become smart. Don't complain, the teacher is not telling properly, not this. If you ask questions, next day they will prepare more and come to class. Okay, are you doing that? Say yes or no. Okay, all the best. Okay, already you have heard morning, so we are having a lot of future. So try to learn well. First 2 years in your career is very, very important. Don't leave not 1% of your syllabus. Don't read anything for marks. Okay, so if you are learning properly, so that it will be useful for entire your career. Okay, and now thank you for coming all the way from Bangalore and sharing your knowledge to all our students and participants and my colleagues. Thank you, Ramana. Now I request Naidu sir, Manjula ma'am, and Satyanarayan sir, Mayuri madam, please join us to honor our guest, Anand.